Hey, what is up? It is Wednesday, June 1st, 2022. Happy June. Welcome to the first real month of summer, or at least the first month where summer happens to be a thing. It is hot here today, and it's a perfect day to do algorithms, right? No, maybe, I don't know. Anyway, welcome to Coding with Shaft, or Shaft to Algo Guy, whatever you prefer. I've gotten feedback about both, and people like both, so I'm gonna go with either or, depending on how I feel in the day. Okay, cool. So today we are going to do a very, very popular Leetcode problem. It's at easy, and at this point in time, I wanted to focus mostly on mediums, but I will make an exception for blind 75 problems, which this is a blind 75 problem called lowest common ancestor of a binary search tree. If you've done any kind of algorithm study at all, you've seen this problem before, okay? And it's good to know how to negotiate it because it is a problem which has a very practical use case in computer science. It's used to narrow down nodes on a graph in many situations when you're doing computer vision, when you're doing ray tracing, when you're doing searching for specific items in a database that has a tree-like structure or a file system. LCA type algorithms are very useful in that situation. So this is probably the simplest version of that, right? And what we're interested in is can we do it in this very simple binary tree case, right? So given a binary search tree BST, find the lowest common ancestor LCA of two nodes in the BST. According to the definition of LCA in Wikipedia, the lowest common ancestor is defined between two nodes P and Q, and the lowest node in T that has both P and Q as descendants, right? Where we allow a node to be a descendant of itself. Okay, so basically, if we take two nodes, let's say, look at the input, it's P and Q, and we have the root. So this is the tree with root 6. If we take two nodes, like let's say 0 and 8, right? What's the lowest common ancestor of 0 and 8? Well, it says is the defined between two nodes as the lowest node in T that has both P and Q as descendants. So that would be 0 has, the lowest node that has 0 and 8 as a descendant is 6. Okay, it happens to be the root. What about 3 and 5? Well, the lowest node happens to be 4. Okay, and remember, this is a binary search tree. The important thing to note is the binary search tree aspect. There's probably algorithms for just plain old binary tree searching for lowest common ancestor, but what we'll be doing is we will be using the binary search tree property to solve this problem. Okay, so how do we come to a solution? So first, it's good to talk out your solutions, and let's see how do we know that 6 is the lowest common ancestor between 0 and 8, right? Well, I mean, in the binary search tree property, if we take an arbitrary number, right, and we try to determine where it should be in the tree. For example, where should 8 be in this tree? Like, let's say I have this tree, I want to find 8. 8 would be to the right. Where would 6 be, and where would 6 be? 6 be is at the root. Where would 2 be, or 4 be, or 5 be? They would all be to the left tree. Okay, so anything less than 6 would be to the left tree. Anything greater than 6 would be to the greater or equal, depending on your definition, would be to the right tree. So basically, we want to find, and I think at this point we're assuming all nodes are unique. So okay, so this is important because if all nodes were not unique, our algorithm would not be as straightforward. Okay, so again, this is the simplest case, and remember to always check your assumptions when you're starting the problem. P and Q will exist in the tree. Also, it's guaranteed that P and Q will exist in the tree, so you should ask this question before starting. And the nodes value is also useful, but not super important in this case. But the size is important because that will constrict how we solve this problem. So what are we looking for? When we say P and Q have to have an ancestor, one has to be less than the root, and the other has to be greater than the root. So basically, we need to find a situation, right, where one where p is less or q is less than the root, and q or p is greater than the root. So that's why, how can we traverse this tree to find that situation? Well, first we will look for, we'll have to know which path to go down, either the right or the left. If we go down the right, how do we go down the right to search a subsequent nested tree? Well, we're looking for a situation where both p and q is less than or is greater than the node to the right, so we'll traverse the right. If it's less than, then p and q will be in the left subtree. Wherever a situation that we find that p is less than or equal to the root and q is greater than or equal to the root, then we know we have our lowest common ancestor, because that's going to be the only situation that we'll be able to get to, right? Like that's how we get to where we're trying to go, right? Because then that will say that's the definition of the ancestor, and it will be lowest, because you'll always get to the situation when you're searching a binary search tree such that you get to the place where you can diverge between values at its lowest point. Okay, to show you how this works, right? So let's say first we want to go to the right subtree. Check if p and q is in the right. So if p dot val is greater than root dot val. Oh, okay, first of all, I want to do I don't want to jump to coding without talking about how my approach is going to work out. Tree node root, tree node p, tree node q. Okay, I'm going to write a recursive function that I'm calling LCA, and you'll see in a minute why the return types are what they are. Val is greater than root dot val. So check if both nodes are in the right tree, and q dot val is greater than root dot val. So now we're checking if the nodes are in the right subtree. That's important, both nodes. So we haven't found a divergence point yet. Else, if p dot val is less than root dot val and q dot val less than root dot val, then we're checking if both are in the left tree. Left, right? Because we want to see if the divergence point lies in the left tree. So we're checking if the divergence point is first in the right. If not, is it in the left tree? Else, we return the deepest point at which they've diverged. So you'll see how I'm defining these parameters here. So I could do this many ways, but I want to do this way to be more certain. I'm calling this LCA. So I'm going to assign the LCA as soon as it's found and return. I don't need the return here, but you get it. That's basically what's happening. So how do you recurse? So if LCA root dot right p q, so if the divergence point isn't found yet, and we're going to check the left and right subtrees, so we check if first if they're in the right subtree. If not, then we go to the left, and there you go. And now let's write out our main function. New tree node. This is my return value, my way of capturing a return value in a DFS. So q LCA return LCA 0. Okay, so I'll explain this in a second, but let's just make sure this works. Okay, cool. So basically what's happening here, again, we are checking if both are greater, strictly greater, because we want to definitely know if the element's in the right subtree. Otherwise, we're checking if both are strictly less, because this will definitely guarantee that we're in the left subtree, that we have to search for the divergence point in the left subtree. Now, all the other conditions indicate that we have a root. And why is that? Because if we're less than or equal to 1 and the other is less than, that means the root, based on the original condition, the node is a descendant of itself. If we have one is greater than or equal to and the other is just greater than, then the root is, or less than, sorry, then the root is still the other root is still a descendant of itself, and thus the lowest common ancestor. Okay, so that's why this condition becomes easy. If this wasn't true, then the condition would be more complicated. But this is a constraint of the problem, so this makes this easier. Okay, so that's it for today. I hope you enjoyed this video. I hope you found it useful. Please like, subscribe, and comment if you did. And I will catch you next time. Happy coding, and stay safe and stay rugged. See ya.